So thank you for coming to my talk today. And my goal is to help you take your first early baby steps along the path to becoming a distributed systems wizard. You ready for that? All right, so first, I'm going to talk about why distributed systems. Seems kind of an esoteric concept. Why? Why talk about that? And then I'm going to drill into some of the innate difficulties that distributed systems engineers have when they're trying to solve the problem of building very complex, scalable, reliable distributed systems. And then finally, I'm going to talk a bit more about an open source solution that my company develops called Golem, which promises to radically simplify the way you build and operate and maintain distributed systems. And it happens to be built on the WebAssembly component model for those of you who attended the keynote this morning. Why distributed systems? Well, how many of the engineers in this room work on distributed systems at your day job? Just by a quick show of, whoa, half the audience works on distributed systems? Wow. Well, this is LambdaConf after all, so shouldn't be too surprised. Let's talk about what that means. In order to understand a distributed system, it helps to understand the opposite of a distributed system, which is a centralized system. And what is a centralized system? Well, it's characterized by the ability to update the entire state of the system in a manner that's atomic and consistent. Atomic just means it happens as a singular thing, and consistent means anyone who reads data from that system at any point in time is just going to see the same correct view of the data. What is a distributed system? Well, a distributed system is basically any system which does not have that ability to update the entire state of the system atomically and consistently. And it doesn't have that ability because instead of the state being located in one place, like on one machine, in one linear block of memory, for example, it's been scattered, typically across a network. And so you lose that ability to do atomic consistent updates. All right, are you ready for wizard school? This is your first chance to take your step number 2 and step number 3 of becoming a distributed systems engineer. Take a look at this system here. We have requests coming in, responses going out, and we have some stateful logic running on a single machine. Is this system, according to my definitions, is it centralized or distributed? What do you think? Centralized, right? Because it's logic, stateful logic, it is stateful, right? So it's updating things in memory and that is affecting requests and responses, but it's all happening on a single node. So those changes can be made atomically and consistently using many different techniques that we have for, locks, STM, et cetera. This is no problem. This is basically a centralized system. How about this one? We have request response coming in, then we have stateless logic running on a machine, maybe more than one machine, and then all these machines are talking to a relational database management system that provides us with ACID guarantees. Is this a centralized system or a distributed system? Centralized, that's right. Yeah, it's effectively centralized because basically it's like we took our logic out and peeled it away from where we're storing the state, but that doesn't matter, right? We haven't changed the fundamental nature of this centralized system. How about this one? We have our stateless logic as before, and we're talking to a database, which we use to store state, and then we're talking to a 100% stateless API. And I can tell you what that means if you really want to know, but basically it means it's every call to any API always returns the same data for the same input. Is this system centralized or distributed? Centralized. It's kind of surprising this one's centralized, isn't it? Because we've got 3 different things here, but it's still centralized. You could sort of see that conceptually if you take that stateless API and just inline it into the app. Right? It reduces to the other one. Okay, now let's make one tiny little change to that diagram. Make that API stateful. Is this system centralized or distributed? It is, it's distributed. We've suddenly moved from centralized system where problems are easy to solve because we can atomically update states in a consistent way, to a distributed system in which that's not so easy anymore. Congratulations. You have attained level 1 of becoming a distributed systems wizard. There's 3 levels. Let's see if we can get to all 3 of them today. All right, so how many, knowing what you know now about the definition of a distributed system, how many of you work on distributed systems at your day job? Even more hands than before. Virtually every hand went up. Why? Distributed systems are really common. They're just incredibly common. And many of us work, if we call an API that is stateful and we also call a database, congratulations, you are a distributed systems engineer. And when you sign up for that, there are many problems that we're going to see that come along for the ride that you have to think about. So what is the trouble with distributed systems? Well, in a centralized system, it's very simple, relatively speaking, to achieve atomicity and consistency because all that state is located in one location. However, the moment we move to a distributed system, and this is kind of the simplest possible distributed system that you might actually relate with, it becomes extremely challenging. Let's say we want to store an order in the database and also call the payment processor and charge someone's credit card for that order, right? E-commerce app like Amazon.com. How are we going to do that atomically and consistently? This is a major problem, and it's probably a problem you've had before. Whether or not you recognized it and solved it, who knows? But it probably is a problem that you have faced at some point in your career, or your recent career, actually. And that's a very simple, like the most elementary distributed system, and that doesn't reflect the systems we actually build. The systems we build don't just talk to a payment processor and a relational database. They talk to, vector database for AI stuff, blob storage for big data, 20 different APIs, and then, of course, at least one relational database, and probably a NoSQL database and a cache and all these other different things. Our systems are distributed to a massive degree. If you want to become more abstract, and sometimes it really does help to abstract things so you can forget the details that can be confusing and just focus on the most simple possible elements that make up a given problem, then really the most general problem in distributed systems is dealing with distributed state. So we have the state of our distributed thing, and remember think of the state of the entire world, right? So the bank account with money in it, that's part of the state of our distributed system. And that's not our system, that's someone else's system, but that has to be interacted with by the payment processor. And then we've got all these other different systems. Think of the state of the whole world here. So anyway, we take and we distribute that state among all these different systems, subsystems, and we want to make changes across all of these different subsystems in a way that's atomic and consistent. If you want to forget all the details and just focus on the essentials, that is the most general possible problem in distributed systems programming. And you might not think about it because you think APIs are about doing things, right? About charging a user's credit card or doing this and that. That's actually not quite true. You charge the user's credit card, what is that? That's an update to some piece of state somewhere. That's all it is. You dispatch the order to the warehouse for fulfillment. That's just updating some state somewhere, some piece of memory somewhere. And yeah, people do something based on that state, but fundamentally it's just updating state. All right, back to wizard school. You ready for this? You aced the last one, so I have confidence in you. Let's say we want to update state on n different nodes. And our first idea is, let's just make a for loop. We're going to run through and we're going to update state on every individual node. Is this a valid solution to the distributed systems problem? No, not even close, right? We are so far away from that. It fails both atomicity and consistency. So let's try to be a little more clever, but not too clever, and say, oh, we're going to go along and we're going to have the ability to lock every different subsystem. So no changes can occur while we lock it, and then we'll have the ability to unlock it. And so we're going to lock a node, and then we're going to make the update, and then we're going to unlock it. Is this a valid solution? Is it? Look at where the lock's occurring. The lock is occurring right before and after each individual update. So what have we failed to achieve here? We're not making all of the updates in an atomic fashion. We're making each individual update in an atomic fashion. Maybe. I mean, there's some other problems with this, but fundamentally, the major problem with this is that we're not making all of the updates in an atomic and consistent fashion. We can fix that, right? Maybe. Well, we're just gonna, for each over all the nodes, we'll lock all of them, and then we'll make all our updates, and then we'll unlock all of them. Simple, right? Have we solved it? Is this a valid solution? You probably want to say yes, but you're also thinking no. Well, I mean, one obvious problem that stands out here is locks aren't compositional. So if you actually try to build a solution based on this, then 2 different attempts to update the state of the distributed system would end up deadlocking because the locks were arranged in different orders. So, and you might think that there's a simple solution to that. There is, and the simple solution doesn't perform. It's horrendous. You could never use it. And then there's very complicated solutions to that problem that might perform better, but they're really, really nasty. And then we have a also very fundamental problem. What happens if the code that's doing all these locks and then doing all the updates and then doing all the unlocks, what happens if that code fails somewhere in the middle? The server could die, a network could go, CPU could catch fire, all these things are valid possibilities. Then we're left in a permanently deadlocked state. That's it. Our system will never make any more progress. So this is very far. It's closer, but it's still very far away from a solution to the distributed systems problem. All right, well, I don't know if I should give you that diploma. I think I will give it to you, okay? You made it to level 2. It's harder, though, to make it to level 2, but don't worry, level 3 will be easier, I hope. All right, well, we still haven't solved any problems, though, right? We've explored some of the issues that arise when we're trying to make atomic and consistent updates to a bunch of different subsystems, but what we're really looking for here is a solution to this problem. What is the solution? Well, it is actually a manifestation of something that is extremely well studied in computer science called the consensus problem. Insert wicked laugh. The consensus problem can be stated as follows. If we have a distributed system of independent agents, how do we get them all to come to consensus on a given proposed value? How do we get them to agree? Someone will propose some sort of change to, or you could think about it as a change in the state to a distributed system. That's a nice intuitive way to think about that. It tends to be modeled in a more elementary fashion, but I like to think about it as someone's proposing a change to the state of the distributed system, and all these different systems need to agree on what that change is. It turns out, even though it's very simple to define this problem, it's really frickin' hard to solve it. And one of the problems is first off, we have to come up with an algorithm for consensus that is correct and can actually perform. So don't be thinking global locks that lock the state of everything independently and then we all do some sort of vote. Don't think that's not going to work. It has to be correct, and there's lots of things that we mean by correct. It has to be convergent and whatnot. It has to have all these different properties. It has to have no bugs, and it has to perform reasonably well for the system we're building. And that's very challenging. But that's not all we have to deal with. No. We have to deal with failure. So once we built this consensus algorithm that can work on these independent agents, then we still have the problem that any one of these agents can fail at any time for any reason halfway through any process. And that throws a gigantic wrench into any sort of solution you can come up with. This makes any relatively simple algorithm, which we could come up with a simple algorithm to solve consensus, and it would be just blown to smithereens by the fact that any node in the system can fail for any reason at any time, part of the way through any process. And then beyond that, we have to deal with this other problem called the partitioning challenge. And this happens when we have this distributed system, and because of a network problem. Some of the nodes in this system can't see the other ones. They can't communicate. They can't talk to each other. And that can happen at any point in time. As we're trying to achieve consensus on something, there could be a network partition. And to make matters even worse, network partitions cannot be distinguished from failures. How do you tell? Did all those nodes in orange fail? Or can we just not talk to them right now? In general, we can't tell the difference between a failure and a partition. So we've got lots and lots of challenges to solve this problem. And fortunately, this is so well studied, there are solutions out there, and they are very widely implemented in most programming languages, and they form the basis of nearly every distributed system out there, distributed infrastructure. So if you want to look at Kubernetes, or you want to look at, take your MongoDB, or whatever system you're looking at, they use what's called a distributed consensus algorithm. And one of the leading ones is Paxos. And Paxos is sort of a very flexible system that allows you to do a lot of trade-offs and still arrive at consensus in a way that makes sense for your use case. And then there's Raft, which is much simpler and more preferred, but not quite as flexible as Paxos. It sort of forces you to do consensus in a more restricted way. It doesn't matter what solution you choose, though. You're going to run into some fundamental limitations here. And these limitations have been described as the CAP theorem. These are not the only limitations you run into, but CAP theorem is probably the most famous, which basically says that when you're building a distributed system, you don't get to choose all possible properties that you would definitely want out of a consensus algorithm. You're going to have to make trade-offs between a consistency and availability and partition tolerance. In other words, you actually, literally, you cannot get everything you want out of a consensus algorithm. You will make trade-offs. And which trade-offs you make, of course, depend on what you're going to be using this distributed consensus or distributed system for. Well, that's a mess. That's a gigantic mess. And I know what you're thinking right now. You're thinking that the solution to all these problems has to involve a big buff-looking golem, right? No, you're not thinking that? Well, that's okay. No worries. Allow me to introduce you to Golem. And Golem is an open source serverless platform that simplifies the development, deployment, and operation of scalable and reliable distributed systems. So if you're building a distributed system that has to be very reliable and highly scalable, Golem makes that, I would say, 10 times, even potentially 100 times simpler than any legacy approach out there, by far. And I'm going to give you some very specific examples. If you went to Afzal's talk on Golem Timeline, you already saw a really great example yesterday. All right, so what is a Golem app? Well, the fundamental building block of every Golem application is this thing you were introduced to moments ago called a WebAssembly component. And that's reasonably good terminology. We build our applications out of components, and we plug these components together, and they talk to each other and so forth. So we build our Golem apps out of components. And the vision, the long-term vision for WebAssembly is that at some point you'll just be able to go to your build tool or package manager or compiler, and you'll just flip on a switch. And instead of building whatever you build now, at the end of that packaging or compilation process, what's going to come out is a WebAssembly component. Like right now, you build your Go program and you get an exe that you run. But flip a switch and you get a .wasm that you can also run, but you run with a system that has the ability to execute WASM components. And it's not true that a WebAssembly component is merely an arbitrary blob of your own code written in whatever language you want, compiled to WASM. There's actually an extra detail that turns out to be very important to understanding things like Golem, and that is every WASM component is allowed to have a public API. And you can think of this public API as being a subset of your code that you want to make available to the outside for purposes of calling. When you compile to an EXE, you have one of these. It's called the main function. And it's pretty simple. You go home, void main or int main, whatever, that takes the arguments of command line arguments, and that's it. That's your one sort of public function from a EXE. WebAssembly is way more powerful than that because you're allowed to say, I want to export all these different functions, and all of them use types that are native in my programming language. You do this using something called WIT, which WIT can be thought of as the WebAssembly component model's version of protobuf. Right? Protobuf we use to define interfaces, but these interfaces are sort of not necessarily idiomatic in our programming language, and WebAssembly is trying to introduce something that is idiomatic and can scale to handle the full range of features that we need when we're building our applications out of components. And you might think, I don't want to have to learn WIT, just like I don't want to have to learn protobuf, and I feel your pain, for sure. And I think over time you're going to see code-first approaches that allow you to, we're going to be working on one for Rust. In fact, I don't see Yarrow here, but if he were here, I would point to him and put him in oh, there he is. Right. That man there is doing this for Rust, right? So at some point, you just come along and add an annotation or an attribute or whatever to some piece of code that you want to export. You don't change the types you're using. You don't change anything. You just say, hey, I want to make this function or this class or this interface or this trait or this struct or this enum or whatever it is accessible to the outside world. Isn't that amazing? It's an amazing idea, No JSON serialization, no protobuf serialization, just, hey, this is what I want to export from the code that I have written using whatever libraries and frameworks I choose in whatever programming language I want. All right, so given that components are the building blocks of Golem applications, and that components are not just sort of compiled code, but also they're like compiled code with some of your data types and functions exported for outside use, what does it look like to build serverless apps on Golem? Well, let's take a look at what it looks like to build sort of typical serverful application. So serverful application, you might build it by constructing an app or a server, adding a bunch of middleware, adding a bunch of routes, implementing route handlers, and then you spin up a server that listens on a certain port, and it handles incoming requests, and then it dispatches every incoming request to the appropriate handler based on the route pattern. Now, that's classic serverful programming. It looks a little different if you're doing gRPC or GraphQL, but it's basically the same stuff, different details. How about serverless apps with AWS Lambda? So if you're using serverless apps on AWS Lambda or something similar to it, then you just build some function, and that function processes events, and those events could be request events. And so you look at those details, and then you decide to handle it in whatever way you want, and you return the result. And the nice thing about this from a development, there's bad things about this from a development perspective as well. Serverless is not current modern day serverless is not a solution to 100% of everything we need to do. It's more like 20%. I think Golem takes that 20% and pushes it to 100%. But right now, 20%, let's say. The nice thing about it is you take this function, you plop it into the cloud, boom. And you don't worry about scaling or servers or encryption or any of that other stuff that you specify at the level of the cloud. You can focus on your business logic here. And that's why serverless is growing so fast. It's growing really, really fast. It's going to be a $40 billion industry before long. All right, so back to Golem. What does it look like when we're building serverless apps with Golem? Well, this is the really fascinating thing here. You just write code. That's it. You just write ordinary code. There's no request, there's no response, there's nothing like that. There's just writing code. And you write code using whatever programming language you want, whatever libraries and frameworks you want, ordinary code. The only difference is you say, hey, I want to export this function, or this data type, or this class, or interface, or whatever. And you can do that with a checkout. Here I have add to shopping carts. Here I have a checkout function that handles checkout for a user on an e-commerce site. It's anything you want. Right? As a developer, I like programming. But I do not like writing glue code. I don't like writing serialization stuff. I don't like dealing with HTTP requests and responses. I want to write business logic. I want to focus on the good, meaty part of the problem, and all these other stuff that's getting in our way and slowing us down, like Brian said earlier today. Why should we be dealing with that stuff? And that's the Golem model, is just write ordinary code. You don't need any of that other stuff. And then how do you do work in a Golem application? Well, Golem has this concept called a worker. And a worker is nothing more than a running instance of one of your components. And it has a unique identifier, which could be like a request ID or something like that, or it could be related to a user's shopping cart or a user or an auction, or it depends on what you're building with that ID, if it has any meaning at all, and what that meaning is. But fundamentally, a worker is just a running instance of a component. And because it is running, right, it's not an exe. Like a component is a lot like an exe. It's more like the process that is actually running in your operating system that you see in Task Manager, or when you hit PS, type PS in your command prompt, and you see it's actually running. And in that running process, it has state. And not only does it have state, which is in memory, it's like heap and stack and all that stuff, your variables and whatnot, but it also has a public API that's defined by WIT. So that's what a worker is a running instance of a component that has its own in-memory state, just like any running process does, any running program does, and a public API that's been defined by WIT that makes certain features of that running process accessible to the outside world. And then the fundamental unit that triggers computation in a Golem application is when you go try to call a function, an exported function, on a certain worker. That's the fundamental trigger in Golem applications. You call a function on a certain worker. And again, that worker could be a new worker created per request, or it could be a more like persistent worker that's dedicated to managing a particular user's data, or whatever. That's up to you to decide. But the fundamental way you trigger computation in Golem is by calling a function on a certain worker. And of course, when you call that function, you have to supply it with parameters, which are typed because of the use of the WIT specification there. Those are typed. And you can actually access this invocation functionality through, right now, HTTP. I think you could probably do gRPC, a little work. And then eventually we'll have some other mechanism that's sort of more native to access that. And basically you can stand up any sort of API you want whose functionality is implemented in terms of functions that you export on your workers. All right, so what is this programming paradigm built on the WebAssembly component model buy us? It gives us some superpowers. And people don't even believe sometimes when I tell them what you get out of using Golem. They're in disbelief. They're like, that's not possible. I don't believe you. I don't believe the words coming out of your mouth, but it is true, I assure you. Number one superpower you get from deploying your WASM components on Golem as opposed to somewhere else is you get reliable workers. And that definition of reliability is extremely strong. What a reliable worker is a worker who will survive any sort of catastrophic external failure without any disruption there'll be a sort of, bit of latency, but without any disruption in service or computation. It means if your worker is, for example, processing the checkout for a given user, and that machine catches fire, then It doesn't matter. That last state of your worker before the fire happened will be recreated on a new node, and your running program will continue from the exact line of code that it left off on. And it will be allowed to complete that checkout process. This happens if there's a catastrophic server failure, or if Kubernetes kills the pod that this server is running in, or it doesn't matter how this thing dies, your workers will continue to run transparently. From your perspective, it's like you're programming on an invincible machine that never goes down. Nothing can take it down. That's why we sometimes say Golem makes your workers invincible. Obviously, they can still die because of bugs in your own code or errors you didn't handle. We can't help you write better code, sorry. But we can help you deal with all those failures that are caused from outside your application, external failures. And we can make sure you never have to even think about that. And then also, reliable communication. So if you have one worker talking to another worker in a Golem cluster, then you get 100% reliable communication, exactly once semantics. And that means you call into another worker, it's going to happen. It's not going to fail, ever. You're always going to get back the typed result that you expect from interacting with that worker. All right, so how does this work? If we pull back the curtain and do a deep dive into this technology, how does it actually work? It works something like this. Your worker is running, and it has all this in-memory state. And by state, you should be thinking heap, stack, registers, instruction pointer. I don't know if you know what those are, but basically when your program is running at some arbitrary point, there's just a lot of state associated with that. And you should be thinking full state, right? Maximum state. There's a lot of state associated with it. And your program is going to do something, like it's going to make a request to an API, or it's going to talk to the database, or a cache, or a file system, or config, or whatever your application is going to do. And that's going to go through, in the beautiful thing about one of the beautiful things about WASM, is that anytime you try to do something involving the real world, you have to go through functionality provided to you by a host. It's basically sandboxed. And that sandboxing allows us to, every time you try to do one of these external activities, instead of actually going and talking to the file system or the network, you actually go to something called the Golem virtual host. And the Golem virtual host mostly just passes requests along to the real host, the operating system. But it also does some other very important things that I'll talk about in a second here. What it does is when it gets an incoming request, it will record that interaction. Well, actually, if it gets an incoming request and the Golem virtual host is not in this special mode called playback, which happens during recovery, then it will go to the real host. And when it comes back from the real host, the result, that will be recorded in, first off, short-term persistence, and then eventually in long-term persistence. And then there might be some automatic retries that happen, and then eventually that goes back to the application. Okay, so this is the Golem virtual host, which sits on top of the real host, but from the perspective of your WASM application, this is just the operating system you're talking to. You're telling the operating system to do all these network calls and stuff. You don't know any different. And as a result, we're able to offer this recording and playback functionality, which allows us to automatically recover something in the event of a failure. So if one of the nodes in a Golem cluster goes down, we know all the workers that were being executed on there. And so what we can do is we can take those workers and we can say, okay, you're going to be restored here, you're going to be restored here, the other ones will be restored here. And then we can recover the state of those running workers by basically folding over this log of external I/O events that we call the op log, catching up your program state to the exact moment before the failure occurred. And that is transparent from the outside world. So from the outside world's perspective, you call in, you make a call, something catastrophic happens midway through, you don't even see it. There's no way to even observe that. Because that computation, that running computation was shifted, recovered on a new machine where the result was successfully produced. All right, so now that you know the two really cool superpowers that Golem gives us, which are reliable workers and reliable communication, we can go back to our earlier discussion and we can ask the question, how does Golem solve the distributed state problem? It doesn't. Sorry. Nope. That would be too magical. Golem's pretty magical, but it's not that magical. And I'm going to argue that doesn't matter. It doesn't matter at all. Why? Because, number one, distributing state is really hard. Every time you take up state that wants to be consistent and atomic and you chop it up into little pieces and you put them across the network, you've signed up for a huge load of difficulties just by doing that. But then what makes that problem so insanely difficult is handling failures. The fact that any different subsystem can go away for any reason at any time in the middle of anything. And not just that, but handling partitions, right? Got to handle network partitions as well. So dealing with all of this is impossible. Not literally impossible, because obviously we do it, but it is not an easy thing. And that's why the number of correct distributed systems out there, I mean like databases, right? Not applications that you build, which are also distributed, but which don't have to be as rigorous as a database. But like a database that's distributed over many nodes, those things are not easy to build. They are extraordinarily difficult to get correct. I've said before, and I'll say again today, that the class of technological solution to which Golem belongs, which is called durable execution, it definitely does not solve all problems in distributed systems engineering. For sure not. However, it does make all solutions possible. And not just possible, but practical for you and I to do. And reasonable. We can reason about these things. We can understand them. We can build stronger guarantees on top of those two superpowers that Golem gives us. I'll give you an example of common distributed systems problems that Golem makes almost impossibly easy. An example is you're writing a checkout routine for an e-commerce app and you want to do all 7 things. Right, if you try to do that using Lambda, you've made broken code. Your code's not going to work, right? Because sometimes it's going to check and reserve inventory, going to process the payment, and then that Lambda's going to die. The node will go down, or it'll reach a timeout limit, and Amazon will shut it down. Something will happen, and your system, your distributed system, will be in an inconsistent state. You've charged the user for something that's never going to arrive at their front door. You write that same code on Golem, and it's just naive code, right? It just does one thing after another. There's nothing fancy there. It's just ordinary code written in any programming language you want that can compile to WebAssembly. You deploy that on Golem, and magically, that will almost run like a transaction in a database. If step number 1 happens, step number 2, 3, 4, 5, 6, and 7 will also happen. Now, along the way, you might have to deal with sort of, domain errors, right? You might process the user's credit card and find out that it's been denied because of suspected fraud. And you have to handle that in your app in any ordinary way, but you don't have to worry about infrastructure failures or network failure or anything like that. Those are gone. You can just focus on your business logic. And Golem makes this entire class of sort of very reliable mission-critical APIs and sort of workflows, long-lived workflows, and all that stuff. It makes it impossibly easy, with one caveat that I don't have time to drill into now, but this is very, very solid. And then at the flip side, let's think big picture and think, well, what if we were building a distributed SQL database? This is one of the biggest challenges in distributed systems, building something that gives us ACID guarantees for any SQL query that's distributed on thousands of nodes. Good luck building that. in one developer lifetime. I mean, you can do it actually, but it's a lot of work. And there's a lot of complexity that goes into building anything that is as rigorous and precise as that. But using Golem, we can at least think about how this might be possible and actually quite reasonable. We use one worker. First off, we shard all the data in the database. We shard it by row ID, for example. Maybe we shard by table, right? So we take our table and we chop it up into shards given by ranges of primary key. And we assign every shard to a worker. The worker runs forever. It can't fail. And all communication to that worker will be 100% reliable. So each worker handles one shard's worth of data. We ask Golem, this is not a feature we support now. It's a feature we know we need to support, but we ask Golem to keep those workers far away from each other in the Golem cluster. Why? Because if one node in the Golem cluster goes down, we don't want it to take down too many shards. So we want to sort of disperse that. We want non-locality. And then every time someone runs a query on this database, we spin up a new worker that's always going to run to completion. The queries are going to be 100% reliable. And that worker handles the task of coordinating updates to whatever rows the database has to handle. Okay, you should look at this and think, this is hard. It's not easy. Because we've got to deal with consistency and atomicity and whatnot, database level guarantees, but there's a whole host of things that we don't have to deal with. And if you were building this using any other way, you could add to the problems we have here a whole book of problems that you would have to solve. And then another great example that if you didn't see yesterday, I encourage you to check out the talk when it hits YouTube, is this project called Timeline, or Timeline Golem Timeline. It is an attempt to take a paper that defines a compositional way of describing queries over event-oriented data. That's a very hard problem. And you can write lots of custom code in Flink, one-off custom code that's not composable and hard to maintain and finicky. And Flink and Spark and all these other systems, it's not very satisfying. It's not like writing a simple SQL query that does exactly what you want. And Timeline is an attempt to bring that to event-oriented data, where the events are ordered in linear chronological history and whatnot. It's very compositional. It allows you to express extremely complicated queries in a very simple and elegant and understandable way. And Afzal's done a great job of showing how it takes this ridiculously hard problem and makes it reasonable to solve. Not trivial, but reasonable to solve on Golem. All right, we are about out of time, so we're going to go to Wizard School one last time. And I'm going to ask the question, what is the most reasonable way to solve any problem in distributed systems programming? Use Golem, yes. There you go. Congratulations. You are now a wizard in distributed systems programming. So you've reached the final level. In summary, distributed systems are eating the world. And there's lots of reasons for that, but software reuse and the fact that everything is networked and if you think about like global software as being a single entity, the part that we write is very small and it has to talk to all the other parts in the world. And as software eats more and more of the world and AI lets it eat even more of the world, is like everything is going to be software defined at some point, which means everything is going to be a distributed system, even though it mostly is today. Building correct distributed systems is very, very hard because of the difficulty doing atomic and consistent updates in systems with partition state. And open source Golem, it may not solve every problem in distributed systems programming. There's still a lot of work left for you to solve, at least in the case of building a database. But it does solve the hardest problem, which is the reliability problem. Reliable workers, reliable communication. And given those building blocks, you don't have to worry about that, and you can just work on computer science or business logic or whatever it is you want to work on. You don't have to think about the infrastructure anymore. All right, so that's all I have for you. I want to thank the organizers, the speakers and sponsors and attendees of this conference. If you want to check out Golem, I encourage you to. It's 100% open source, and you can find out more on golem.cloud. And tomorrow we are having a special Golem hackathon. So if you want to build an application on Golem, And then you're going to get one-on-one hands assistance. The hackathon's entirely free, and we're giving away some nice prizes, I think like MacBook Pro and type stuff for people who build cool applications. So if you want to hack on, and not just Golem, there's going to be Restate and DBoss participating, which are other excellent durable execution platforms. So you should head there tomorrow and find out what all the hype is about regarding durable execution. It is a new way of building highly reliable systems. And in my opinion, it's going to not only extend the reach of serverless, but it's also going to usher in a new era where small teams can deliver incredible value. And that's where things are headed. Right? In the future, we do more with less. Going back to the theme of Brian Sletton's keynote this morning, we do more with less. And durable execution is a key enabling technology. And WebAssembly component model, I believe, as well. So check it out. Give me any feedback, and thank you again for attending my talk. I appreciate that.